Yeah, welcome now. Uh, we will be learning today simulation using the RAT-FRAC distillation unit module in DWSIM. Okay. Myself, Dr. C.V. Nageshwara Rao. I am Associate Professor in the Department of Chemical Engineering, Gayatri Vidya Parishad College of Engineering. I have done a faculty development course under the training of Spoken Tutorial IIT Mumbai. Now, as you can see, the screen which is actually opened on my system, my laptop, is a DWSIM platform. So we are launching this. I have launched the DWSIM in my system. Now we'll go to the new, or we'll go to the file, and then I say new file. So new chemical process model. So I click on the new chemical process model. So it automatically, first of all, opens the simulation configuration wizard. So we are at this place. So it says, welcome to the simulation configuration wizard. And then going ahead. So we take up benzene and toluene, benzene and toluene, as the binary mixture, liquid mixture for our particular operation. See, these two are, same functional group. So Raoult's law will definitely work. But, for the sake of, utilizing a, what you call, thermodynamic property package, I would like to take up any other package which enables every time whenever we choose one particular system, it automatically tells us about which thermodynamic package can be chosen. So see, it is not actually showing an RTL, it is showing Raoult's law, Swab-Redlich-Kwong, right? And then suppose say if I have miscellaneous, these are the various unit, thermodynamic packages which are available. So as of now, see, because I thought NRTL would be enabled, but it is actually judging and telling us these are the things which you can actually adopt. So let me take Swab-Redlich-Kwong, hopefully, or Raoult's law, because we are accustomed to this Raoult's law. I'll take Raoult's law. Okay, add. By default, phase equilibrium is chosen as VLE, and then we'll go to the next. Okay. Now, instead of taking the default SI, I'll take this C5, wherein we can check the temperature, pressure is atmospheres, and mass flow rate, molar flow rate, and many things are available here, right? And this volumetric flow rate, let us keep this as liters per hour. Okay, liters per hour, and then say, okay, fine, finish. Now we came to our flow sheet window. Now let me go to the column, and then you can see ChemSep column, distillation column, absorption extraction column, shortcut column, three-phase reactive PR PPB design column, right? So I will take DC column here, which is actually rigorous distillation column, and automatically you can see this displays as if we are seeing a real-time distillation operation in our industry, right? So this is, you need to adjust a little bit the streams here, because to look more, or more understandability. So I take up like this, and then these are the two products. So the two products, and there are two energy streams, there are two products. So the stream one, let us name it as feed. Okay. So this is binary feed. So we'll see it as feed. And then the top stream 2, I name it as distillate. Distillate. Okay. And the bottom one is, this is bottoms. Let me say bottoms, right? So this is or you can say residue or bottoms, like that. So let us say distillate and residue, right? Actually, overhead, if you say overhead product, it should be bottoms product. So if I rename it as residue, it will be more logical. And the energy stream also, let us actually rename energy stream. This we say condenser heat load. We can say this. Okay. And E2, we can say reboiler heat load. Reboiler heat load. So this is how it is defined now. So we are ready with our column nomenclature now. And now let us give some inputs to our streams. Now I'll take this to see. I think you can see it. I think you're able to see the right. Now I'll go to the feed, and then in that feed already package is chosen, stream conditions 25 degrees centigrade and 1 atmosphere. We will choose molar flow to be as 100 kilomoles per hour, and it is coming to 9,798.64 liters per hour. Okay. Okay, it's a huge one, right? Done. And we'll go to the compound amounts. We say benzene to be a 60% molar percent and toluene to be as 40%. And we say accept changes, right? So this is, we have defined the feed conditions now. And we can also say, that means we can say that feed is entering at bubble point, feed is entering at dew point. Many changes can be done. Now I click on the distillation column itself. Now you can see this one I give trace to be as 21, and then column top pressure is given as 1 atmosphere. We can give column pressure drop. Suppose at 0.1, if I give, there will be a pressure drop in that, right? And then go to the specifications. Specifications reflux ratio, it is given as 2.5. Let me give it as 2.31. Okay. So this is total reflux ratio. Condenser C, partial, total, partial, full reflux. And in that we have defined what? The reflux ratio here. There can be other parameters which you can specify also. And then let me go to the reboiler here. In the reboiler, product molar flow. See, we have said toluene to be as 40%. In the bottom, what we don't want benzene to be more. So in the benzene, we want only 1%. Suppose say I take compound fraction in this product stream and I click benzene and this is molar. I say it is 0.01 and then I press enter. See, you need to give some time so that it is taking. That means it is the value which you are entering is resisting or not. And one more thing, this operation on distillation column, I tried with latest versions. There are what do you call new programs added, new convergence criteria is taken up. So, but I am comfortable presently with 8.4.3 operating in distillation column. So that is the reason I'm operating it in 8.4.3, wherein with this type of imports and the distillation column, I can see in this version to be as as we see in the industry scenario. So that is the reason I am choosing this 8.4.3 version of this. So now we are ready with giving inputs. No, we are not yet ready. We have given the number of stages, reflux ratio is given, specification reflux ratio is given, and the reboiler, we have given benzene in the bottom product. That means light key in the residue to be as 0.01. That means light keys in our case is benzene. Now go to the stages. There are stages available here. We have 21 stages. You can see. Now go to the connections. See stages. Let me check whether I can see. If we go down like this, it will be seen. Now go to the connections. In the connections, what is given is port 1 feed is already given. So I say I change this port to somewhere around 6. Okay, I can do that. This is port, means this is nothing but a nozzle type where my feed enters. So products, see the products by default distillate is distillate, bottoms is residue. And the duties, you can see condenser heat load and reboiler heat load. There are no side draws in this. Now the stream stage connections. The feed tray, suppose say there are 21 trays, we say roughly around 9th tray. See, you should remember one thing in this particular simulation exercise or DWSIM or simulation packages, even the condenser and reboiler are also given names. So that means if I say 21 trays, there are actually 19 trays inside the distillation operation. So we have given this and don't do anything else. There is nothing to actually do anything and just leave it like that. And then we are ready with all the data given. So let us see. General conditions. Number of stages we have given 21. Condenser top pressure we have given 1. Column pressure drop is 0.1. And maximum number of iterations. This iterations part we will take up. And specifications, condenser, we have said total condenser, reflux ratio is 2.31. And the reboiler, we said benzene, that means light key in the bottom products should be only 1%, that is 0.01%. And the stages part, we have seen stages and connections. We have given this connections for this, right? Stream connections and stage, this particular stream stage associations. That means feed tray enters at what tray? That is what you have to give. See, okay, connections, stream connections, like that. So feeds, I have given port number 6. You can give port number 7, port number 5, whatever it is. And the products are also mentioned here. Now, our specification of the entire simulation exercise is done. Now, once again, let us see what is the input data. 100 kilomoles per hour and compound amounts, you can see 60% and 40% molar flow fraction. So now I think I have done with my this thing. Let me see whether it solves or not. See, now you can see what is giving. Solver reached the maximum number of iterations without converging. So bubble point problem is coming here. So I say this, and then let us increase these iterations, and then let me try to solve it again, whether it solves or not. Otherwise, you have to change the feed conditions and then look at conditions. It is running. Is it running? Yeah, I think it is running. Okay. It is not converging. I'll go to the feed. Okay. I say, yes. Now see, I made number of iterations. I've increased number of iterations. It has taken some time to actually calculate. But see, let us see whether the results part, we have to see the results part. I click on the distillation column. I go to the results. Now see the results here, right? Condenser duty, reboiler duty, condenser specification value, condenser specification calculated, reboiler specification value 0.01, reboiler specification calculated how much? 0.009. And that means we have achieved, boss. This iterations taken 12, estimated height is 11,500 mm. That means 11 meters height is there, and estimated diameter is 1723 millimeter. That is around 1.73 meters. That means we view temperature and profile. Now see, this is temperature, and there is a pressure also. See, this pressure is also changing from, we said there is a pressure drop, right? So now you can see the table also here like this. And this is the graph, and then we can see the flows, component fractions. Every stage to stage, we can actually look at this particular parameter. Now see, stage wise, what is the pressure, temperature, all the properties are estimated here, and then it is giving us the data. But okay, fine. But what is that we want to look at? We want to look at the output, whether we have achieved or not, right? So let me go to this place. Let me go to this place. Yeah. Now, where is our output? Our output is lying somewhere here. So the residue. In the residue, now look at the residue. It is toluene is 99%. You can see benzene is 0.0099%. Wow, we have literally achieved our simulation. Now the feed condition is this 100 kilomoles per hour, and you can see the let me actually come down. You can see 60%, 40%, and then you can see this is achieved. And how many moles here? Moles here is wait a minute. This is moles here is 40 moles kilomoles per hour, and moles here is 59.65 kilomoles per hour. Totally 100 kilomoles per hour. We have achieved our simulation, right? And let me add a material, article total material property. In this, we take up the feed, temperature, pressure, mass flow, molar flow. And let me check the whether I have molar fractions here. I come down. Yeah. molar fraction overall liquid. Yeah, that's it done. So I add distillate, I add residue, and then let us check whether it is possible or not. So molar fraction overall liquid, it is giving this one only, but we require benzene, right? So molar fraction will come down. Yeah, molar fraction overall benzene. You can see this, So that we will try to see, and toluene also we can take. See, molar fraction overall liquid toluene. Now let us see whether, yeah, now you can see. This is what is our result with respect to the simulation of the distillation column to separate a binary mixture. Hope you have understood the step-by-step procedure. How did I do? Please do subscribe so that you can get more videos, learning videos like that. I'll be exploring things and then make the content ready for you. And furthermore, please give me the comments so that I can improve upon making such videos.